Jill has given us a previous very interesting talk on EV batteries, and she is the Director of Advanced Materials Technologies New Zealand Limited and an expert on refractory materials, particularly for the steel industry. She has an honours degree in zoology, and her honours thesis was on energy return on energy invested in birds. And this has come in handy a few decades later because it has become such an item of interest in human energy systems. Jill has participated in transition engineering activities, including helping to organise the Carbon Transition Convergence event in Auckland a couple or 3 years ago. At present, she is consulting to an Israeli company called Helios on green steel. And I'm pretty sure if anything approaching business as usual as we know it is going on in 2130, they will be using steel. So I think this is a highly relevant and topical thing to learn some more about. So, Jill, I hope everyone's concentration's holding up, and I look forward to.
Okay, so my interest in steel originated because I worked for BHP Steel, and I worked for New Zealand Steel after they were bought by BHP. And actually, it was a job I really enjoyed. And the disconnect between being a sort of environmentalist but really enjoying a job in steel was something, you know, I had to work with. So when carbon emissions became a problem and there started to be solutions being mentioned, I obviously would become interested in that. But, you know, all the interest has been sort of in the traditionally first world country steelmaking. So that's why I've sort of wondered whether it was just a fantasy of first world producers that green steel was going to have a future in the energy transition. Anyway, so steelmaking trend, just over the top of my comments here. I'm just having to hide your faces here. Anyway, steelmaking is the 6th largest emitter of CO2, and it's also, probably more importantly, it's actually the fastest growing industrial emitter since the year 2000. The global production of steel is enormous, and 50% of that is from China. So it's about 2 billion tonnes a year. In addition to the iron-making carbon dioxide release, the mining of coking coal often is in very methane-rich mines, and so they also are a significant producer of methane, which adds 27% of the impact of steel to the 20-year climate impact. When the Paris Agreement was signed, this had a significant impact on the projected tonnes of steel that could be made. Otherwise, we'd have to find another way of making it which doesn't emit CO2. So as you can see, in 2015, we're making 2.8 million tonnes of carbon dioxide, and it needs to go down from 1.8 tonnes of carbon dioxide per tonne of steel down to 0.2. At the same time, it needs to ramp up production in order to meet demand. And steel, can we live without steel? Well, it's something that I think it's very difficult for anybody who has been alive in the last 100 years to imagine a world without steel as a sort of foundational material. It's also a very large part of our transition to renewable energies, and wind turbines and even solar plants, they're all requiring a lot of steel. And this is a dilemma, not just for industrial carbonisation, but for all climate action. So anything that we are doing to reduce our reliance on coal and fossil fuels usually has a large impact in terms of its footprint, and a lot of that is to do with the steel it uses. There are structural alternatives, but fairly limited in terms of the sort of size of structures. I probably don't have to tell you any of that. But I think we're in a situation where we're starting to suffer from the impacts of climate change, and this is leading us down a route of wanting to build more resilient structures, which could actually take more steel and rather than less. So rather than reducing our consumption, we may be increasing our consumption in order to deal with climate change. And this has been suggested as a sort of doom loop where the worse climate change impacts we feel, we emit ever more carbon dioxide trying to deal with them. So the options for decarbonisation are, firstly, the most obvious one is business as usual, but capture the carbon. Or you could use other reductants, and natural gas is a lower carbon footprint, but doesn't solve the problem. You can use hydrogen or a mixture of hydrogen and natural gas, other carbon-based reductants, molten oxide electrolysis, electrowinning, which is not really being pursued, and other metals, which is what I'm involved in. The other way, there's also other innovative refining techniques, which I might mention later. I don't know how many of you are familiar with the blast furnace, but it's a huge, it's like 4-story high furnace that's very well enclosed. And basically, they're sort of like a black box with inputs and outputs. And because of the way they're constructed, they have a very long lifespan. And in fact, the oldest blast furnace is over 50 years old now. So basically, if you're going to invest in them, it's investing in the long term, and ones that might have been built 20 years ago, those companies are still thinking they're going to have 20 years left in them. So there are a number of options for carbon capture, and I'm not really that familiar with them, but there has been many that have tried. One of the problems with carbon capture, and some of these are capturing the carbon and wanting to put it back as carbon monoxide into the furnace. But one of the problems with blast furnaces and with replacing the fuel is that the coke is actually a structural element, and the coke burden is the structure of the coke burden is a really important part of iron making, and it's really, you cannot do without that in a blast furnace. It also doesn't solve the problems to do with mining coking coal. Now, the cost of capture has been one of the issues, and this graph shows you, if you remember that we wanted to, the average was what, 1,800 kilograms of carbon dioxide per ton of steel. And so in order to capture most of it, you need to be in this sort of area. And then there's a carbon cost to actually capturing it. And there hasn't been a financial incentive to do that because the cost of carbon hasn't been enough. And when I wrote this, 1 ton of carbon had reached its highest value ever at 100 euro. But I don't know if you saw the news today, but our local carbon market actually closed without trading today because the cost of carbon was below the lower barrier. So there's not much incentive to capture the carbon if you can buy carbon credits. and also electricity. You can use recycled waste heat and generate electricity in order to make it less costly to recover the carbon dioxide, but there's still quite a quite a penalty in terms of energy consumption. So one of the other options was to replace the coke with a biocarbon, which is a sort of, in my sort of opinion, is that there's not really low carbon emissions, in that you have to rely on growing that forest, and it's a bit of an accounting thing rather than an actual transition away from a carbon-based steelmaking. So this is something that's being trialled in Australia, and initially Carbonscape were interested but have pivoted to battery graphite, but it's basically a pyrolysis of woody waste, and it's briquetted and used in the blast furnaces. The advantage is it doesn't have many impurities, but I don't know whether we'd have enough woody waste. If we look at Gisborne, maybe we have plenty of woody waste for this sort of thing, but it's not going to last in the long term. So the other option is new reductants and techniques, and most of these materials are for additions to the arc furnace, and I chose an old photograph of an arc furnace which looks a bit more like what I'm used to, fairly dirty, gassy, noisy, and this is potentially the future of green steelmaking. So the feedstock would be directly reduced iron. So that means it's not melted and it's turned into metallic iron at sort of below 1,000 degrees. Now this could be with hydrogen, but the really important thing to notice with hydrogen is that that's an endothermic reaction. So you have to heat the hydrogen, you have to heat the pellets in order to drive that reaction. You could use carbon monoxide, and that's what is used with natural gas and other processes. And that's an exothermic reaction. So, you know, you just have to have enough heat for it to start, and it'll generate its own heat. Solid carbon, which is sort of like what happens with New Zealand Steel's processes, and with the Helios process is using alkali metal, which again is an exothermic reaction. So you only have to heat it up to a few hundred degrees and the reaction takes care of itself. So these are made in a shaft furnace, which are like a sort of small blast furnace, and that the lumps feeding through the top, reducing gas. There's a bed of lumps at the bottom, and the gases pass through that and reduce the ore on the surface. But it's really very, very dependent on temperature, and so the kinetics of it are very complicated, and that's complicated by the difference in ore composition and impurities. And because if the case of hydrogen, because it's an endothermic reaction, and you need to add heat, and the reaction is changing all the time, it's very hard to control the temperature profile in that reaction. So this is the sort of dream of direct reduced iron, which is the hybrid hybrid hydrogen direct reduction plant in Sweden. Their advantages is that they have the biggest iron ore mine in the world and the biggest iron ore supply in the world. They have a very high grade titanomagnetite, and they have plenty of hydroelectricity, and therefore they can really make some gains with hydrogen steelmaking. On the other hand, you have a Port Lisa is a Trinidad Midrex plant, and that has been operating for 20 years and so forth, and it's been using a variety of gases, natural gas, hydrogen, and so forth. And that's sort of the reality of a direct reduction plant rather than a shiny Swedish model. And it has been supplying electric arc furnaces for many years. And it's put there possibly because of cheap energy, possibly slack environmental safeguards and that sort of thing. So, the issue with hydrogen steelmaking is it is reliant on high-grade ores, which have to be above 65% Fe oxides. And the reason for that is that the the impurities are retained in the direct reduced iron. There's no opportunity in that process to get rid of those. And so as a pellet heat to an arc furnace, then if it's high in gangue, then you have a lot of slag and you have a low tap weight, and it's economically and, well, production-wise, it doesn't work very well. The other thing about hydrogen is that it requires, if it's going to be green, it requires renewable electricity, and the conversion efficiency at the electrolyzer is at best 75%. So a large consumer of electricity. And as I said before, hydrogen reduction of iron is endothermic. And so the pellets have to be heated and the gas has to be heated before it even enters the shaft furnace. It's also very highly temperature dependent, and if the temperature is varying, you get problems of low reduction rates, sticking of the iron to the shaft furnace, and the hydrogen can reduce the outside of the particles and stop any more hydrogen from diffusing in. The other thing, which I actually just learned today, was that because you need to have a certain amount of hydrogen in the reaction chamber, then actually there's a lot, like 40% of the waste gas stream is actually unreacted hydrogen. And so there's that cost of producing the hydrogen, it's going off in the waste stream. And so you have to recover that. So if you're Midrex, you put out a very attractive looking process diagram, the hydrogen, the heater, heating up the pellets and so forth. In reality, the process looks more like this, where and mostly that is characterized by the kilowatt hours used to create the heat, to create the hydrogen, to heat the pellets up here, heat the hydrogen, and then recover the hydrogen afterwards. And I'll go to the next one. Anyway, I'll talk about it. I was expecting another slide, but anyway, this is a graph. It's a bit old now, but it's of the ore grades that are available. And the message here is that ore grades are generally not high enough for hydrogen steelmaking, because there would be too much gangue left over. And in the United States, they use an ore called taconite, which is actually something that they have to refine before it even goes to the blast furnace. It's a very low iron grade, and they have to carry out a lot of benefaction. And that's what's used in the United States. And that's one reason why the United States is one of the best recyclers of scrap steel, is because their ore grades are so poor. The largest exporter of iron is Australia, and as you can see, the ore grades tend to be below what is required for hydrogen steel making. And so this is quite a problem. This is a slide on the impact of adding direct reduced iron to arc furnace charge. So when there's no direct reduced iron, so they're just using 100% scrap, the CO2 emissions are what, 400 kilograms. So that's, if you remember that the other one was like 1800 for a blast furnace, so that's a considerable reduction. So here we are, yeah, 1800 for a blast furnace. As you increase the directly reduced iron contents, then those emissions are going up, and that's based on ores that are 65% iron. As if they use ores that are less than 65% iron, then basically you've lost your emissions advantage. So one of the solutions to deal with low iron ores has been to add on to the end of the process something which is a DRI smelting furnace. Now, I don't know how many of you would have been familiar with New Zealand Steel's melters, but I was quite shocked when I saw this, because this looks like a New Zealand Steel melter, nearly exactly. And it is not something that I would ever expect that anyone would add on to a green steel making process, because it has to be run in carbon monoxide atmosphere. And it's very prone to water leaks, product leaks, and having worked on those for quite a number of years, they're not what I would call a reliable production unit. Particularly, they have great difficulty with the tap holes. So I didn't feel this is something that's being promoted, and ArcelorMittal have apparently committed themselves to buying some of a similar smelter, and that sort of horrifies me. Another fairly advanced project is that of Boston Metals, which this is, sorry about the poor quality, this is a diagram of their process, which is a molten oxide electrolysis. So I'll show you on the next slide. There's the bath of iron. They have a cathode, the molten oxide is the electrolyte, and the anode is this in the center here. I also find this quite quite crazy in that they show the tapping of liquid iron. Don't seem to show any tapping of any of the slag that's produced, and that will just build up. And it also shows oxygen bubbles. I would think that that's just atmosphere that they're removing. It has incredibly well resourced backers, so it's been given millions of dollars by people like Bill Gates and so forth. So although I can see a lot of problems, they're extremely well resourced. And one of the problems I see with it is that sort of material is not going to be easily contained in a refractory, because of the amount of iron oxide in that electrolyte is going to be extremely corrosive. And they're looking at very high temperatures, 1700 degrees, and the performance of this has got to be sort of questionable. I mean, that's what I would say. The other innovative refining technologies, they sort of amuse me as well, because we used to work on those back in Australia in the 1980s. They were introduced, and that high smelt was there was a project in Western Australia where they built one of these, discovered that the thing wears out like crazy and closed it down again. Yet there's still investment in these from some sectors. Anyway, so in the New Zealand context is pretty much run by Australia, because BlueScope Steel is the Australian owners of New Zealand, and they have pretty much a philosophy that is not ready, and as a result they're rebuilding the number 6 blast furnace at Port Kembla, which would put them on track to be still using a blast furnace in 30 years' time, which, you know, we well over the 2050 that we're supposed to be really out of these sort of technologies. So anyway, this has caused a lot of consternation in Australia, and it also means that in New Zealand, I think that we won't be getting a lot of investment from BlueScope Steel, because it wouldn't make sense for them to be, on one hand, relining their blast furnace, and on the other hand, investing in New Zealand in green steel making. So another webinar that was just recently was on the decarbonising Australian steel production and where it is heading. And I think he probably wasn't really sure where it was heading either. And that's basically the way where it is. It was recently written up as being on a bridge to nowhere. And as a result of sort of public pressure, it's now starting to perhaps threaten that it's not actually going to reline the blast furnace after all. Even though they've spent millions of dollars on it already, they seem to be pressuring the government to give them a bit of a hand up as far as emissions legislations. And then, but more interestingly for us, New Zealand Steel is still getting free carbon credits from our governments. It made a profit of $340 million, and yet our taxpayers paid it $117 million in carbon credits. But the more recent news is that they're now considering putting an arc furnace in, which is going back to the future, because when I started there was an arc furnace at New Zealand Steel. And of course, it started with an arc furnace. Now, the reason for that is that at the moment, all of our domestic scrap is collected up by Pacific recyclers and exported. So we do not process any external scrap at New Zealand Steel. Any scrap that they use on site is what's been generated on site. And that amounts to like 550,000 tonnes of scrap steel, whereas the production of steel products from New Zealand Steel is only 640,000 tonnes, although it's capable of more. And they actually sell pig iron to arc furnaces around the world, rather than using it themselves. So that 640,000 tonnes is purely a market decision. They can make like up to 900,000 tonnes. So, and I'm looking at this today. I found this article from, I don't know if anybody is familiar with Chris Bumby. He's been investigating hydrogen steel making using New Zealand iron sands for quite a while now. And they've just a recent paper on the potential. It makes very interesting reading if you're into green steel making. And one of the benefits is same with Sweden, we have good renewable electricity, and that's going to be the decider as to whether green steelmaking is worth it or not. So this is a diagram of their reactor. Pretty standard. But they have been able to drive the cost down because they have been able to recycle hydrogen very, very well. And so their energy requirements are sort of low compared to other hydrogen steelmaking. And we also have the advantage of having an ore body which is amenable to this and which can be affected beforehand to have an ore quality that doesn't cause problems later on. So anyway, what I'm working on is actually a company by the name of Helios in Israel, which is replacing the card, which is using sodium metal to reduce the iron. And I can't say too much about it because I've got their overheads. This is what I'm allowed to sort of speak about, but sodium metal is very effective at scavenging the oxygen from iron at very low temperatures of sort of around 400 degrees. And sorry, I don't know if someone was asking a question there. So the other aspect is the sodium can be reclaimed and re-metallized, and can be taken somewhere else and is independent of the process. So the real attraction for me is the iron making between 400 and 700 degrees, and that gives a lot more possibilities as far as containment and not having to deal with liquid gang products, because those won't form at those temperatures. It doesn't have any, the only carbon emissions would be to do with any electricity that's needed to power it. It's an exothermic reaction, so you just need to heat it up to a few hundred degrees, and then it starts on its own, and you add obviously you need to add the energy back later when you recover the sodium metal, but it doesn't have the process control problems. And it also can be used within any ores. So back to whether it's a first world dream. Sorry. One of the issues is that we have the second largest steelmaking company in the world, ArcelorMittal. It's creating great media hype with its commitment to green steel in Europe, ordering hydrogen reduction plants and melters, as I showed before. At the same time, it's commissioning blast furnaces in India. And so actually its carbon footprint would actually increase despite its uptake of green steel in Europe. So I'd also like to acknowledge this paper this PhD thesis by Valentin Vogel. And his is really interesting in that he approaches it from a social aspect of how you equitably allocate resources. So say green steel takes an awful lot of energy, which is okay if you're in the north of Sweden, but it's taking electricity from consumers in other parts of the world. So it's not really, can't be seen as a just transition. I don't know if you saw an article that was posted by Mike Joy today on incumbent league transitions, and this green steel transition is as an incumbent-led transition, and then it's sort of hoping for incremental changes, incremental improvements that will maintain their market share of product, but in a way that's more palatable to consumers and addresses the political needs, evades carbon taxes, allows them to have free carbon credits because of their plans and so forth. But it doesn't address long-term sustainability, particularly if you're looking at having to build a huge number of hydrogen electrolyzers using platinum electrodes in order to create the hydrogen. It also means that we're not getting action on demand side, and even if we're still using steel, perhaps we can use it with a bit more forethought and not just chucking a whole heap in, which seems to be the way of, less design, more materials is what I've heard it described. It also shifts the problem from one of being direct carbon dioxide emissions up the chain to the electricity supply, which could mean in some countries that you end up building more or relying more on fossil fuel power plants. Instead, it needs to be seen as a part of a larger societal shift to a more sustainable way of living, a more circular economy, use less sort of economy. But in order to have that, it needs to have more input than just the big producers of steel, which is what it is today. The large producers are pretty much leading the conversation, and those other options are not being sort of discussed. So that's it.
Okay, well, thanks very much, Jill. That's a vast amount of knowledge there. And does anyone have some questions?
Yeah, I got a question. You right at the beginning, you showed a graph on the demand in 2050. I guess that is the demand that the steel industry is forecasting. There might be other things that are happening in the meantime, and that will never come to that huge demand. It might just impossible to supply it. And you, in your last slides, you were saying there might be more incumbent-led transitions and so on. I think the whole issue is a big task for transition engineering to figure out a way how society can do all the things, creating more renewable energy generation with actually less steel and less concrete and so on. And so just going by the steel industry's figure might be the wrong thing to approach the whole problem.
Well, it is, but unfortunately, the demand is still growing, and it was still projected to grow in the third world, and you come against all those issues of equitable access to resources and equitable access to all the things that we enjoy here without increasing emissions. So
yeah.
I have one question. I remember from my school chemistry classes that sodium was pretty scary stuff. You just had to chuck it in a bucket of water and there was a most enormous reaction. And I wonder, I think you did touch on the energetics of using sodium, but are there kind of practical concerns as well with that kind of a process?
Well, I think did they use like sodium powder?
In school chemistry?
In school chemistry?
No, the teacher would put the piece of sodium under oil and he would take a pocket knife and shave a bit off, and he had a huge bucket of water, and then he'd chuck the shaving into the little piece into the bucket of water. So No, it wasn't a powder, it was a lump of sodium metal.
Okay. Well, I think the presentations I've been with Helios, I think they address that first of all. And no, I mean there isn't that problem of it being a terrifyingly reactive metal. You can just use it, without throwing it into buckets of water. And it's not an issue of just having a bit of moisture. You need a lot of water. So I haven't seen that as a problem.
Could I
Right.
follow up on the sodium? Just thinking about where would sodium come from? And have you factored in the cost of getting the sodium in your calculations of efficiency?
Yeah, so I mean that's not the part of the project that I'm involved with, except that work has all been done and I have got the information on those, on the access. So it's not a new industry. So the sodium metal can be acquired very easily and very cheaply. And then it's just a matter of recovering it each time.
So, Jill, does it mean that the sodium materials requirements wouldn't be a constraint to that type of industry growing quite a lot?
I don't know. I don't think so, but it's not being projected as a billion-ton industry. So, I mean, I think that we have to go both ways, really. We have to, we do have to contract our steel use. And part of it would be, I mean, a lot of it is actually recycling. And that's one reason to favour an arc furnace with direct reduced iron is you have infinite ability to use either 100% direct reduced iron or 100% scrap and anything in between. And hopefully, in the future, then there's a lot more scrap to cycle through that. So you wouldn't need to be producing enormous amounts of sodium or enormous amounts of iron ore like we are today.
Thanks, Jill. You talked of the different purities of iron ores in different countries, and I spent a few weeks at Schefferville on the Quebec-Labrador border in Canada, which I think has quite a high purity. So it's interesting to see that you had quite a high purity for Canadian iron ores. But how would you characterise the West Coast New Zealand iron sand?
Well, I think they're pretty much on the cusp of high purity. The West Coast iron sand, it does depend where it's come from, and they have some infiltrations of clay and so forth. But the really good thing about the iron sand is that it can be magnetically separated. And the amount of separation that they do in the mine site in New Zealand Steel, I mean, I have been there a few times, is pretty minimal compared to what they might do in other like hematite mines, and what they do with the taconite mines in the US is extraordinary sort of benefaction. And so the New Zealand Steel iron sands could be easily benefacted to a higher extent. The problem with the iron sands is the titanium, and in Chris Bumby's and the others paper, they actually oxidize the iron sand before this process in order to remove the titanium. But I mean, I only just saw that article today and I haven't studied it thoroughly, but they have a lot more to say about the suitability of the iron sands and the treatment required.
And I'd heard someone saying that at Benbrook they'd used an electric process, but would that just be for the recycling of the steel?
So the electric process is the melter, which is like the melter I showed halfway through the presentation. So the direct reduction process is in the multi-hearth furnaces and then the kilns. and that is transferred to the melters. And the whole purpose of the melters is to melt it and remove the slag. So because they don't do a lot of beneficiation, and so they need the melters to remove it again as slag. And it's not something I would recommend. I would recommend benefaction before it gets to that stage, because the melters are not a great production unit.
And so when we look across, well, New Zealand's industries that use a lot of coal, and okay, so we have dairy factories that heat milk to turn it into milk powder using coal, or this cement as well. So it seems, is it that steel has a higher capital cost for the plant than these other industries? Does it seem to be?
I think with New Zealand Steel, I think they are maybe the second largest consumer, but they're right up there. I think possibly the one that has least options is the cement plant at the moment. So for Fonterra, there are other ways of drying milk. It's a pretty easy process. But for Glenbrook, it's it's not just a source of heat; it's the reductant. And at the moment, it would be pretty difficult to replace anything in the kilns. You would have to replace the whole primary plants, or the iron making plant.
Yeah, so it's expected to be quite expensive then to change that then.
Yeah, but it sort of has to be done. The melters they're both over 20 years old, and they would not be expected to last that long. And so actually they're overdue to be replaced. They're just being bumbling along, being repaired all the time. So at some stage, BlueScope has to make a call on New Zealand Steel. And it's something that it's been talking about for literally decades. And they wrote off the value of the primary plants 20 years ago. So it's something that comes up all the time, but nobody makes a decision on it.
Okay, so it's not like the aluminium smelter, which keeps on threatening to close down to
it is a bit,
lower.
Yeah.
Okay. So it does do that too. Okay, so that'll be part of the decision making if they have a large capital building project for.
Yeah, well, that's what we, if they're putting in an arc furnace, they could close down everything from the melters back and just put in an arc furnace, just using scrap, as I was thinking. But I don't think they've decided what they're going to do with it, because at the moment they can also sell pig iron from the melters relatively profitably. The problem with scrap is that if you continue using scrap all the time, it starts to build up in various impurities. So they need to build a detinning plant or something to deal with that. So you can't recycle steel infinitely. You have to keep, because you have to keep getting rid of the impurities.
Yeah,
it's interesting looking at some of the carbon calculators getting developed for the building industry, and there tends to be an option in there for recycled steel. So it would be a lot more appealing if we could convince some Australians to invest in an arc furnace here to recycle our steel and create that local option, instead of like having engineers see this appealing drop down option of recycled steel and then realizing that they have to import it from Europe as passing the ship with our scrap going to Europe or Asia to get recycled. So is there anything you think we could do to help advocate for someone investing some money in an arc furnace here?
I suppose that one of the things is the building industry demanding that recycled product is available. In America, there is a grade of, and it would be a plate grade or a very high grade of steel that's available for use in wind turbines that is certified renewed, recycled and made with renewable energy. But it probably doesn't change the carbon profile of the industry by doing that, because they're going to make a certain amount of steel that way anyway. A lot of their steel is from recycled materials in arc furnaces. So it's just that they've sort of taken a bit aside and put a brand on it. Whereas here, yeah, we are sending away all of our domestic product. So, if there's demand from the building industry, either we want recycled product or else we're going to buy recycled from overseas, then that's something they will probably take notice of, I would think.
Yeah, it's hard as structural engineers. So the MB approach is that we have to estimate our carbon dioxide emissions of our buildings, and we'll have a 10-year time period over which to reduce it to an acceptable level. But we don't know what really is the future of the concrete and the steel. So it makes sense to use timber and to use timber, lots of it, as a way to store carbon, but we still want reinforced concrete foundations, and steel is so useful in so many ways. But just that approach, designers don't really have much influence over the basic material production processes.
One sort of thing that I think I got, Jill, and maybe you can confirm that I got that the hydrogen process is quite problematic in many ways, and the sodium process looks like being quite a better way of reducing the ore.
Well, the thing is with the hydrogen process is very like a mature process. It's been done for 20 years. There's an enormous amount of work on it. And I think possibly places like Sweden, where they have really good control of their inputs, and they can probably control it quite well. But if you don't have a really good ore source or good control of the process, the inputs, then it's very easy to get into trouble with it. And they have tried using Pilbara iron ore in that process and found it's very problematic with sticking. And so they know that they need to control the temperature very finely, but when you've got a gas that's at a reaction that's endothermic and a gas flow, and I can imagine that temperature control is very dicey.
And on the other hand, the sodium process is not mature. It's
not
still
at all. No.
Not right. No.
No, I mean, it's just it's sort of similar as to I found with Carbonscape, is that you have a really good idea, and I'm quite a fan of Carbonscape, and you have to sell the idea before you can actually really do anything major with it. So it's all sort of in a laboratory scale, and in theory, it can be scaled up because of the work you've done on the background of how you would scale it up. But you have to raise the capital before you can actually do it. And that's quite a break on, it's quite a break on those processes. So Carbonscape has been around for decades, and it's only getting to a pilot plant equipment now. Yet, I felt like it's the process was proved ages ago. And sort of similar with Chris Bumby's hydrogen steelmaking process. I went and had a look at that 10 years ago. And, you know, he sort of has to prove it on paper and then gets to build a pilot plant. And you know, it does actually work as you would expect on paper, but there's an awful lot of background work to do. And that's sort of where they are with the sodium process, in that it looks really good on paper, and I haven't found anything to trip it up yet. So, you know, you're usually looking for, if it sounds good, if it sounds really good, it's probably not. So you look for the problem, and I haven't found what that problem is. If there is one, there may not be one. And you know, the lower temperature is a real bonus for so many reasons. It's so many things that you can do at those temperatures that you can't do at 1,000 degrees or 900 degrees.
Right. Oh, well, thanks very much, Jill. And has anyone got any more questions? Because we've done a solid hour. So yeah, thanks very much for the presentation.
Thank you.
Yeah, thank you.
Very interesting.
And so it's an enormous field at the moment. It's just mind-boggling how much is coming out on that. So we should get some of it here at some stage.
Yeah.
I remember Thomas highlighting in a submission that things like just boilers and stuff have like a 25-year life. So if, like coal-fired things, if the government's phasing them out now, it's a decision that's not going to have an effect for 25 years. I wonder if there could be an argument for saying we need to phase out blast furnaces and sort of get a government ban on new ones, so that at least in 40 years time, you know.
Well, we won't have to get a blast furnace here, but then that's the problem we're having in Australia, is they need to replace that blast furnace number 5. They already had blast furnace number 6, so they closed it down, and they were refurbishing it to take over from number 5. But it's at a time when people are transitioning away from blast furnaces. And in Europe, there's an enormous number of blast furnaces that are going to be needing recommissioning or decommissioning by about 2030. So that's why there's a really big rush on. But as I say, on the one hand, they're transitioning to green steel in Europe, and on the other hand, building blast furnaces in India and China. So.
And is it that it takes a lot less energy and carbon emissions to transport the steel than the production, than the making the steel in the first place?
Sorry, what's with
like the shipping? Like if we have a blast furnace in New Zealand with lots of hydro and wind generation.
Well, we don't have a blast furnace in New Zealand. We have a completely unique process, which is a direct reduction process. We won't find anywhere else in the world, which is using 4 kilns and in a direct reduction mixed with pulverized coal. So the problem with adding scrap to that process is that the oxygen steelmaking vessel can only take like 20% scrap, and they can make that 20% scrap from internal scrap. And the other thing is they actually don't want to make any more than 650,000 tons of steel a year, because they're servicing the domestic market. And it doesn't really make money to export. So basically the production at New Zealand Steel is what our consumption of those products is, remembering that it doesn't make all steel products. So,
yeah, that's helpful.
Yeah. So they closed the arc furnace down in 98 or something. And it was a really old arc furnace, and the dollars per ton for steel coming out of it was very, was very high.
Yeah, then there was the Pacific Steel at Ohuhu, which,
Yeah,
so was that a much
that's
smaller
right.
process?
That was well, it was making different grades. It was making billet products, and that was closed down more recently. But I'm not sure of the economics, but they decided to make billets and flat products in Glenbrook, all from an integrated iron plant supply, and not use any purchased scrap.
Yeah, as designers of reinforced concrete, we noticed that quite a bit when it went from Otahuhu to Glenbrook.
Oh, you did? What did you notice?
Well, we haven't noticed any. I don't think we've noticed any material property changes so much, but we definitely knew when it happened. I think previously there'd been a bigger issue when they went from grade 430 steel to 500 MPa yield strength steel, and then that had problems of if you bend it forward and back too many times, it would fracture. It would,
Yeah, it's made into reinforcing bar at Otahuhu steel, but it's just that it comes from New Zealand Steel's plant as billets. Yeah.